This matrix approach is useful when we solve systems of linear equations. Let me remind you how we do this. So first of all, if we are given system of linear equations like this, for example, let's look at this particular system, we can rewrite it in a matrix form. What is the matrix form of the system? So we can write it as A, X is B, where A is a matrix, consists of corresponding coefficients of x1, x2, and x3. So here the first row is 1, 2, 1, 1, 3, 2, 1, 0, 1. The x is the column vector x1, x2, and x3. This is in fact unknown vector. And b is the vector of the numbers on the right side, 8, 13, and 4. And how we can solve this system? We can multiply both sides of the system by A inverse. So we get A inverse AX is A inverse B. And this thing is just identity. And you can check that identity times X is just X itself. So we obtain that the vector X is A inverse times B. And as we know A inverse from the previous video, we found the A inverse here. So X is A inverse 3 over 2 minus 1, 1 over 2, 1 over 2, 0 minus 1 over 2, minus 3 over 2, 1, 1 over 2, times the column vector B, 8, 13, and 4. So what do we get? We obtain column vector of the following. So 3 over 2 times 8 will be 12 minus 13 plus 2. This is the first term, so this times this. Now this times this will get 4, and in fact, so 1 over 2 times 8 is 4, 0 times 13 is 0, minus 4 times 1 over 2 is 2. And the third term of this vector will be minus 3 over 2 times 8 will be minus 12 plus 13 and plus 2. So what do we get? Here we have minus 1 plus 2 is just 1. 4 minus 2 is 2. And here we have 3. So from this we easily see that x1 is 1, x2 is 2, and x3 is 3. So this is solution of the given system of linear equations. So you see that this matrix approach is quite useful, and now let's see what else we can have for matrices. And the important thing, which in fact determines the answers the question when we have an inverse. In fact, not all matrices, so not all any n times n matrix has an inverse. And this notion of determinant helps us to determine quickly when the matrix has an inverse. Let me introduce the notion of determinant, and the first thing that we do, we define determinant of 2 by 2 matrix. Let's say A, which is A11, A12, A21, and A22. So is, first of all, is defined as absolute value sign determinant, or sometimes you can also see notation like this, determinant of A, and this is A11 times A22 minus A12 times A21. So this is the definition of determinant for 2 by 2 matrix. What if we have 3 by 3 matrix? In the case of 3 by 3 matrix, we can use the following idea, the following property of determinant. So if A is 3 by 3 matrix, so A11, A12, A13, A21, A22, A23, A31, A32, A33. Then the determinant is, we can expand this using the determinant of 2 by 2 matrix as follows. We choose, for example, the first row, and we multiply A11 by the determinant of this matrix, A22, A23, A32, and A33. Then minus this thing by determinant of this matrix which is left. So A12 times A21, A23, A31, A33, and plus 1 A13 times this matrix. So the determinant of this matrix, A21, A22, A31, and A32. So the determinant for 3 by 3 matrix is defined like this. And like this you can define the determinant of any n times n matrix using the same idea. However, there is also a nice algorithm for finding the determinant of 3 by 3 matrix. So what you do, you write the matrix once, and the same matrix, just we repeat the same matrix near this matrix. A12, A22, A31, and A13, A23, A33. And what is the determinant of this is you multiply first these things, and these things. So these things we take with plus sign. So these things we take with plus sign, and the other things, so this diagonal and this diagonal and this diagonal, we take with minus sign. So let me write what it is. So this is A11, A22, A33 plus A12, A23, A31 plus A13, A21, A31, and with minus sign we take A13, A22, A31 minus A12, A21, A33, and minus A11, A23, A32. So this is another useful algorithm how we can quickly find the determinant of the matrix. And let me now show the theorem which answers the questions when a matrix has an inverse. So this is the first important question that we answer today. So the theorem says that if we have, let's say A n times n matrix, then the following statements are equivalent. So the first statement, that A, we say A is singular, and let me explain what it means. Singular, it means that there is A, there is not A inverse. The inverse does not exist. And B, the determinant of A is 0. And also, so this too gives you the criteria when there is an inverse for matrix A. And also we have some other important statements here, that the system, so this is 0, 0 vector, this is matrix, and the unknown vector x has non-trivial solution. solution. Non-trivial means that x is non-zero. Of course, this system has trivial solution, right? If x consists of all zeros, matrix multiplied by this zero will give us zero vector. But this statement says that there is not just trivial solution, but also some other non-trivial solution. Okay? And part D says that the columns of A form a linearly dependent set. Linearly dependent, it means that there are some, not all zeros numbers, say C1, C2, and so on, Cn, so that linear combination of these numbers and the columns of A will give you 0. So linear dependent means that there are numbers C1 and so on, Cn, such that C1 A1 plus C2 A2 and so on plus Cn An is 0, where this A1 and so on An are columns of A. So A consists of columns A1 and so on An. So let's say A1, this is a column, A11, A12, and so on, A1m, A1n. Sorry, we're talking about n times n matrix. And so on. Okay, what else this theorem gives us? Assume that we're given n times n matrix A, and assume that this is singular, so that singular, it means that there is no inverse, or as we know from theorem, the determinant of A is 0. Then we know that the system has non-trivial solution. Has solution, let's say some x0, which is non-zero. And in fact, it follows that for any number, for any constant c, we have that c times x0 is also solution of ax0, right? This can be easily checked. And so this system has infinitely many solutions. So infinitely many solutions. We take arbitrary c and we multiply by x0, we get again a solution. So there are infinitely many solutions. And it means that if we look now at the system Ax is b, this system may have no solutions, depending on b, of course, or may have infinitely many solutions. So you see what conclusion we made from this. If determinant of A is 0, this system may have no solutions or infinitely many solutions. So in this case, we will not have the case when the system has unique solution. And how this infinitely many solutions looks like, if we denote xp, let's say some particular solution of Ax is b, then any solution will be of the form xh plus xp, where xh we say kind of homogeneous solution, because here we have 0 on the right side, we can have the resemblance with the differential equations. So AXH is homogeneous, solution of homogeneous, so this is of the form CX0. So any solution has this form. Let me show you on an example how this thing works. For example, let's look at a system 2, 4, 1, 2, 4, 0, minus 4, minus 8, 1, x1, x2, x3, and this is equal to, let's say, 8, 6, minus 10. And you can see that you can find that if this is matrix A, you can check that determinant of A is 0. And in fact, if you solve this, if we solve using the, let's say, Gauss-Jordan elimination, we get x1 is 3 minus 2s, where s is a parameter, x2 is s, and x3 is 2. And if we write it in the vector form, x1, x2, x3, we get 3 minus 2s, s2, and we can rewrite it as 3, 0, 2 plus s times minus 2, 1, 0. And this will be this kind of our C parameter, our homogeneous solution, and this will be our particular solution. And so this has infinitely many solutions. And also you can notice that the columns of this matrix are indeed linearly dependent. So you can notice that if A1 is the first column, 2, 2 minus 4, A2 is 4, 4, 8, and A3 is 1, 0, 1, then there are numbers C1, C2, C3 such that we'll get 0. So this is 2 times A1 minus A2 plus 0 times A3. Indeed, 2 times A1 will be 4, minus 4 is 0, 4 minus 4 is 0, and minus 8. Minus 8 plus 8 is 0, so we get 0. So it means that A1, A2, and A3 are indeed linearly dependent. So let me summarize everything that we got from this. So we can solve linear systems using the matrix approach. How we do this? We write it first as this system, and then we look at the matrix A. And the answer for the question, how many solutions does this system have, we can get from the determinant of A. If the determinant of A is non-zero, it means that we can find an inverse matrix and do this thing to find X. And we have unique solution in this case. If the determinant is 0, then it means that there is no inverse for the matrix A. And in this case, we know that we may get no solutions or infinitely many solutions depending on B.